very much, and thank you for the opportunity for this idea. It was really fun to kind of go over this material and yeah, and make this up. So yeah, we'll talk about the singularity theorems, and if you went over these papers, you have noticed that it's a theorem at the level of a mathematical theorem. And I'm not going to go to all details of the mathematical rigor. I'm sorry to disappoint whoever expected that, but I'm going to kind of go to discuss the essence of the things, okay, as might be appropriate for this foundation seminar. And so let me start by posing a question that, again, might be very appropriate for the seminar. Why? Why do we even need to discuss singularity theorems in GR? Meaning, it sounds trivial, right? We have a bunch of mass that is experienced only in gravitational attracting force. It will obviously collapse. Why do we even need to discuss singularity theorems? Why don't we discuss singularity theorems in Newtonian mechanics or in other theories? So anyone an idea? Like I'm looking for a simple idea to get the essence of the things.
I think in Newtonian mechanics, singularity theorem is very interesting. I mean, it's a big topic and very difficult topic, whether singularities form or not. I think in body problem. So I would agree with that.
Okay, so people do the okay. So
it's a very different,
but it's a very different.
Even in Newtonian stellar mechanics, I mean,
That's
well,
what I
blow up implosion is all very common to study. Maybe not by physicists, but
So what is okay? Let me pose a different. What is special about singularity theory? Okay, you're the expert. So it's not to you. What is? Why do we need to discuss singularity theorems in GR? It's basically I'm looking for one word answer to this question. So, and I want to I will discuss this question in a moment. I think it's also appropriate to have some historical review of the developments as it reveals the motivation and the idea behind the topic. And through this historical review, I will also kind of try to answer the question that I posed. So we started in 2015, of course, with Einstein's field equations. And soon after the discovery of the Schwarzschild metric that poses the question about the singularity of the horizon. Now, the singularity of the Schwarzschild horizon confused people for a few decades. It wasn't completely settled until much later. In fact, the people tried to understand it, and for example, in 1927, Lemaitre, which is familiar from the FLRW solution, cosmological solution, in fact, he answered this question by studying a solution, which is what we call today Schwarzschild de Sitter, and he argued that the singularity, the Schwarzschild singularity, actually disappeared when you add a cosmological constant. And his point of view was that spherical symmetry is not a real symmetry of the real world, and the static property of Schwarzschild is also not an idealized solution. In practice, there is evolution, and once you add the cosmological constant, the singularity disappears. So we didn't mention the word coordinate singularity as we now understand it, but we definitely understood that it's an artifact. Nevertheless, people still struggle for a couple of decades after that about the meaning of the singularity at the horizon. Einstein himself seemed to have thought that it's a mathematical artifact, So the conclusion is that it seems that people were worried about this issue, but they weren't terribly worried.
Uri,
Yeah,
just on the historical
yeah,
note.
yeah.
So there is this thing called Eddington-Finkelstein coordinates, which
Right.
happily penetrates the
Yeah.
horizon.
Yeah.
Now, Finkelstein is 1950s, but Eddington must have done
That's
it
true,
already.
yeah.
He didn't realize,
He also, yeah, Eddington was part of this.
and he realized that it is not a real singularity.
Yeah, because he found the Eddington.
Yeah.
Thing.
But then what? Nobody else listened to him.
Well, as I also commented on that, but
Okay.
people were not. It wasn't the discussion was not settled. So that's exactly
Yes.
right. But I think that Einstein never believed that it's a physical thing. It's some artifact, but he wasn't. I'll say one more word. One of the reasons they thought that singularities are not physical is that this solution and what was known until then, or back then in these days, was spherically symmetric, and people thought that once you perturb the spherical symmetry, things will become regular. And my impression, it might have been the case also that during the 20s and the 30s, people focused on quantum mechanics and maybe not that, and most effort went there, not to gravity. So that's part of the story, I guess. And indeed, in 1939, Oppenheimer and Snyder published the first singularity theorem of a spherically symmetrical gravitational collapse, and they showed that the singularity formed. I think that was this paper was part of. Actually, it's the reason that Oppenheimer was interested in that is probably due to quantum mechanics and nuclear physics. Few years before that, it arrived a bound together with Volokov, a bound on the mass of a star to form a neutron star. So then the natural question that he faced was what happens if the star is more massive than that, and this is why they were thinking about gravitational collapse. So it originates from an interest in quantum mechanics and nuclear physics, indeed. But still, that was spherically symmetric. So people thought, okay, the real world is not like that. Singularity will not form. It's an idealized situation, and it might be bothersome, but not too much. And this point of view got some confirmation in 1949, where Gödel found a solution known to the Gödel universe, I believe, which is rotating and free of singularities. It's free of singularities, geodesically complete, rotating, although it has some pathologies that are called closed timeline curves, which we'll see will play an important role in the singularity theorem, but it provided a good excuse for people like Einstein and the people around him to not think too hardly about this problem, I guess. April 1955, Einstein died. And a month later, appeared the paper of Uri. That Roshan discussed last week, and I will briefly review today, which is the basis for the singularity theorems. And during this time, a lot of people thought, a lot of young generation started to think about this problem. And as I mentioned, the problem of the singularity seemed to have been tightly related to the problem of rotation. In 1963, Pierre published his the paper with the Kerr solution. And let me complete the timeline, and then I will make some comments. 1965, Penrose's paper on the singularity, And so what I want to emphasize and suggest is that there is a close relation between the discovery of rotating solutions that indeed experience or have a singularity and the development of the singularity theorems. Another motivation, even though Penrose doesn't mention this explicitly as a motivation, it does refer to the Kerr solution, but it doesn't say that that's the motivation. But I'll try to argue that it was definitely in his mind. Another motivation that he mentions explicitly is the development of radio wave astronomy, the discovery of the CMB and quasars, which back then they called it quasi-stellar objects. So that provided experimental motivation to study objects that are not stellar. What I want to argue is that the appearance or the development of solutions, rotating solutions, and the development of the singularity theorem is tied together. In fact, so Penrose in the 60s has a collaborator, whose name is Newman from the Kerr-Newman solution, and in the early 60s they developed what is today known as the Newman-Penrose formalism. And they were actually also part of the effort to find a rotating solution. So a person that worked with Newman told me the following story, that in fact Newman and Penrose were very close to derive a rotating solution. They actually had it, but they had a small mistake. They had some minor sign mistake, and back then there was no Mathematica. They were confused with the sign of the angular momentum. There was some mistake. They sent it to an article, to a journal. The editor of the journal was Alfred Shield, that sent it to his postdoc Roy Kerr. And a month later, a month or 2 months later, the paper of Kerr appeared. So things were really tied together. They were thinking about this, and I'm sure that that's part of the reason that the singularity theorem appeared soon after. It was part of it. Let me also mention that Newman wrote in the same year, actually a few months before Kerr, together with Unti and Tamburino, they founded another solution, which is called Taub-NAT. That was also part of the effort to find a rotating solution. It's not rotating, it has different properties. It's considered pathological because of the appearance of closed timeline curves. And if I have time, I will also mention this solution at the end of this talk. So really the conclusion of this historical perspective is that, by the way, this is 50 years after Einstein. So there was a long period of time. 1915 to 1965 is the same as 1965 to 2015, which is around the year the Black Hole Initiative was formed, right? So what I want to say, I guess, is that it's not a coincidence. Things were there. People were thinking about rotation and singularities. And I want to conclude this historical perspective by answering this question: why? So what is the essence of the singularity theorem in GR? Why is it the angular momentum is so important? Well, in GR we have limits on speeds, so things cannot rotate as fast as we want. If they could, perhaps we could imagine a situation in which the centrifugal force balances the collapse, and that's what people like Einstein had in mind. But no, in GR we have a limit on speeds, and therefore what seems to be the essence of the thing is the tension between causality and having something regular. That's what I wanted to say with this question. And causality also, of course, related to the appearance of an horizon. So So things are, so I think that's my understanding, that's the essence of the thing, and I hope that the experts can can prove my, yeah. Okay, any questions, comments?
How
Common
soon
taste.
was the quasar identified with black hole?
Yeah, it's a good question. I'm not sure, but I guess they just thought that there are objects that are not stellar. We need to explain them. It might be related, but it's a good question. I'm not.
Yeah, around that time. I think
Yeah.
there are two papers, one by Zeldovich and one by Salpeter.
So before Schmidt? Or
Oh, no, it's all after Schmidt.
Okay.
You have to discover the quasar first,
Um,
then show that, it's amazingly luminous and amazingly
rich.
compact.
Yeah.
How the hell do you do it? And, they just said, there is this weird thing that people talk about called black hole. How about that? And then it kind of caught on. So I was wondering, the story about
Yeah.
Newman Penrose
Yes.
writing a paper,
Right.
Schild being the editor,
Yeah.
Kerr being the referee, and Kerr publishing the paper.
Yes.
It sounds very, unethical.
It happens often in science.
It happens often in science. Maybe it shouldn't.
Well, the story. Well, there are some facts, and the story that I told is just a second hand. So
Okay.
it's not a written fact, but.
Okay.
I
The
think
journal will have
that-
records.
What's that?
The journal will have records of these things, and probably by now it
Yeah,
is
yeah.
public.
Yeah. So I think that Penrose received the recognition, but I think that Newman at
Newman,
at some
yeah.
level, maybe I thought that he might have missed some,
Yeah.
that he deserves more recognition. So. Okay, let's move on because I'm running a little bit slow, but okay, so last week, Prashant started I should do with the question, but rather quickly. So let me just summarize because that's an important part of the singularity theorem. So, first of all, we can decompose the metric into we can separate the orthogonal part, the transverse part of the metric to some. So here U is a time-like or null tangent. It's tangent to a time-like geodesic or null, but I will focus on time-like. And H mu is the transverse metric. Then we can define this object, the derivative of mu. So this object essentially, if we have neighboring geodesics, there is a vector that connects them. This vector essentially measures the failure of this vector to be parallel transpose along the geodesic. So it's a property of the space-time, but also of the congruence of geodesics that we choose. And then, as Prashant reviewed last week, this object can be decomposed into trace part, symmetric traceless piece, and anti-symmetric piece. So this is the trace. And theta is called the expansion parameter. Sigma, the symmetric traceless part is called the shear. And omega mu nu, the rotation. I've been very brief because we discussed it last week, but if there are any questions. B obeys certain properties. For example, it's transverse to U, and from the properties of B, one can derive the Ricciardoli equation. Well, that's the Ricciardoli equation. It tells us how the expansion parameter evolves with the affine parameter of the geodesic. In the case of time-like geodesic, that would be the how's it called? I forgot the word.
Proper time.
The proper time, yeah. And the interesting thing about it is that if we set the rotation part to 0, and if we assume this piece here is greater or equal to 0, then the right hand side is smaller or equal than 0.
What's the physical justification for setting omega to 0?
Yeah, it's a good question. It's not completely clear to me. Just this morning, I thought that it might be related to torsion, but I'm not sure. I thought about it just this morning. So, but yeah, it's do you have any another suggestion? What the justification?
I think it's a simplifying choice to look at a particular
Yeah.
congruence that has, I mean, that's hypersurface forming or has omega equal to 0.
Yeah.
Because you don't need to prove what you need to, like the similarity theorems for all congruences. It's
Yeah.
probably sufficient to find one congruence that does it.
Yeah, so one answer is to simplify, but I suspect it might be related to torsion. I'll say something about it at the end.
Actually, related question.
Yeah.
You might have explained this, Prashant. If I look at all the assumptions that Penrose makes, or Penrose and Hawking, which assumption is ruling out the rotation?
No, it's explicitly said.
Does
that
it
it's
actually state?
hypersurface orthogonal.
That's the
explicit-
point.
yes, the explicit-
Hypersurface orthogonal rules out rotation.
Yeah, that's equivalent. Hypersurface orthogonal is equivalent to setting omega to
Okay.
0.
I guess
And
I can't still
yeah,
remember the connection.
Yeah,
So the
exactly.
Frobenius theorem says that if you have a hypersurface forming congruence, then omega will automatically be 0.
Zero. That's where Frobenius comes.
Right.
Okay.
Yeah.
Okay.
But it can't be torsion because there's cases where you satisfy Frobenius's theorem, but you still have torsion.
Oh.
It could be some kind of torsion, but like at least
I
kind
see,
of like
I see.
direction.
Right. It might be, yeah, torsion have more components than this. So it might be a component. Oh, we can discuss it later. I'm not sure about that, but yeah. Another comment that I have is that this is usually referred to as the null, as the strong or null energy condition, strong for the case of time, like null for the case of null vector. But in fact, it's more general. This is called, well, the condition of the curvature, it's actually called time-like convergence condition. So this is called, this is actually called the convergence condition on the curvature. If we commit to Einstein gravity with Einstein equation, that will translate into the strong energy condition. But we don't have to commit to that. Yeah, any questions, comments? So under these assumptions that the rotation is 0 and that the convergence condition is satisfied, we see that the theta, the tau, is smaller or equal to minus 1/3 theta squares. And this equation can be integrated to give 1/theta is larger or equal to 1 over theta 0 plus tau over 3, where theta 0 is theta at tau equal to 0.
Sorry, so you set omega, okay, so you set up some congruence of geodesics.
Yeah.
On some hypersurface, so how do you know that omega remains 0? So I get that you can set it up that it's initially 0. How do you know that it remains 0? Is that,
It's an assumption.
it's a pretty bad assumption if you, I mean, no, I mean, it's an assumption initially, but somehow, how do you propagate it? How do you know that it remains? How do you know that omega remains 0? I mean, that might be where torsion comes in, where maybe you can compute the derivative of omega, and then
Yeah, it's not, yeah.
somehow,
Yeah,
is omega parallel transported? Maybe that's the question. In Einstein gravity.
Yeah, it's a good question. So,
I don't think so, but here the spirit is to say that we have already a congruence that it's not a question of initial data here. We're already looking at a congruence that is assured to be hypersurface forming.
Yeah,
And
but
then
how
the-
do you know that these ever exist?
Yeah, the if you have such a congruence, then what happens to the expansion? That's the sort of question there.
Well, I think there's an equation for omega,
Yeah.
which looks like a derivative of omega along the geodesics is proportional to omega.
Okay, so then if it's 0, then it remains 0.
Yeah.
Yes, but okay, but presumably this uses sort of the torsion frequency, I would imagine, deriving
Yeah.
such an equation.
Right.
No,
Yeah.
so all I'm saying is if omega is 0 initially, it remains 0, but maybe that's where torsion.
yeah, yeah, the comment about torsion is not just something I thought about this one. Yeah, I can do that. So we have this condition, and now we can consider two scenarios. One in which, let's say that at some point, the theta 0, maybe at some point theta is smaller than 0, is negative, then we'll get to theta. Theta will go to infinity, to minus infinity, at some finite time. At a time smaller than this value, theta will reach minus infinity, which means that the finite rays in this congruence will converge together. So at some time, some finite time, they will converge, and this point is called the caustic or focal point. We can consider the other case where at some point theta 0 is larger than 0 is positive, and then we can reach theta goes to plus infinity at some past time. And I want to make a comment that will be part of the singularity theorem. Right now, it might seem a little bit weird, but if it's part of the singularity theorem, we could have a fine-tuned situation or peculiar situation where this is always 0 along the time-like cornel ray. By the way, this is true also. Essentially, this is true also for null geodesics. This would be true. The derivation is a little bit different, but this is essentially true also for null rays. So what I want to say is that there could be imagine a fine-tuned situation where this is exactly 0 along the entire ray. And perhaps this might also be zero. We could have a fine-tuned situation in which theta is zero and stays zero. It's a peculiar, it's not a generic situation, but we could have something like that. And in this case, there will be no constant. Theta will just remain zero. So to avoid this situation, soon we'll see in the singularity theorem, actually in the second singularity theorem of Hawking and Penrose, they need to impose some generality condition that excludes this kind of situation. And that's the origin.
So Uri, you said something now. So the negative theta naught.
Yeah.
Clear that there is a time in the future when
Right.
theta will go to infinity.
Right.
Then you said if theta naught is positive,
Yeah.
then you can go in the past
Right.
and you'll hit a singularity again.
Right.
So there is always a singularity. I mean, is
Yes.
this
Yeah.
either in the future or in the past?
Yeah, if theta zero is positive, then what we will have is that,
Somewhere in the past.
yeah, so on the past things were singular.
Okay,
I should have said this as well.
right, okay. Was that clearly stated in Penrose's paper?
Yes, but very short. I mean, the paper is very,
Paper,
very
I
brief.
know, it's terrible.
It's very, very brief.
Yeah.
But yeah, he's mentioning the formation of the caustic.
One way or the other.
Yes.
It's basically what this is
Yeah,
saying.
exactly.
One way or the other, you'll have a caustic.
Well, okay. So that's a distinction between Penrose paper and Hawking and Penrose. Penrose discusses the formation of
Future,
the singularity
yeah.
in the future.
Right.
So actually, okay, maybe I should take it. Well, the discussion is very brief.
Yeah.
So maybe the statement about the caustic that he makes might also refer to this. But what he has in mind is the future.
It's the future, right. Hawking is very clear.
Yeah.
Yeah, because he's thinking of the Big Bang.
But
and
this
all
is even before. So this
Yeah.
is just like Uri. So the statement,
that. Yeah.
strictly speaking, the statement that Penrose makes might also implies that as well.
Okay.
It's just the direction.
Is the Lyapunov exponent contained within the Ricciarduri equation, the separation of nearby? And you would think that it would actually, you could extract it from this.
Yeah.
Yeah.
Yeah, I guess.
It is, yeah.
Yeah.
In fact, our
Yeah.
the photon shell Lyapunov exponent, you can get it from the JDS deviation equation in Schwarzschild curve. So you can exactly intuition.
Okay, so that's a Ricciarduri equation, and this is called the focusing theorem. It's an essential part in the singularity theorem, but it was known before. And that doesn't mean that there is a physical singularity, just a focal point. So by itself is not a singularity, but it's used in the singularity theorem. And the important concept that Penrose invented is the concept of closed black surfaces. And so that's an important ingredient that Penrose invented in this paper. And this is a surface S that is compact without a boundary, meaning that this is the meaning of the word closed. It's a compact 2D surface. Compact also means that it is finite. We can define it more precisely using in the following way. So it's a compact, it's a surface with two orthogonal families of null rays, K mu plus minus. One is future pointing and the other one is past pointing, such that the expansion parameter of both is smaller than 0. That's the definition of a closed flat surface. And let's see what does it mean.
The product enough. future pointing, right? They're outgoing,
Outgoing and ingoing, both of them future pointing, and both of them converge.
Can I ask you,
Yeah.
so if I wanted to connect to cosmology Friedman models.
Yeah.
How does the scale factor relate to theta? That's a simple thing where sigma is 0. And the expansion factor theta is like the scale factor or inverse?
Well, I think the question is a little bit more involved because theta depends also on the choice of congruence. So it depends on the background, but also on your choice. So you have to specify what is the congruence of finite and null rays. So there is no like, simple answer. You need to run.
I can also just say, if you look at the time like geodesics that are just freely falling,
Right.
then it would be A dot over A.
It's A dot over A.
Theta will be A dot over A.
Exactly.
So what does it mean? What is a closed top surface? Imagine that we have a stationary space-time. That developed in this way. This is, let's say, time t, and this is time t plus dt. Then we can draw this surface and send these two null rays in opposite directions. What we will see is that it's something like that, namely the area of the outgoing null ray will be larger than the original one, and the area of the inner surface is smaller. But in an expanding universe, or let's say in a shrinking, contracting universe, we will have the initial surface and the two other surfaces will be smaller, and the surface is contract if even the larger of this is smaller than the initial, than the area of the initial surface. This is called this is what a trapped surface is. So that's actually the key concept that Penrose invented, and that allowed him to formulate the singularity theorem. So now let me get to the essence of the singularity theorem of 65. And again, I will not show the full mathematical rigor, but I want to get to the essence of the things. So the 1965 singularity theorem, the statement is basically the following. Imagine we have some initial data, so which is described by, so this is the Cauchy surface. That describes the initial the initial boundary conditions for the process of the gravitational collapse. And we have a bunch of matter that are collapsing. Okay, so basically I'm just reproducing the drawing for the paper. So whoever looks at the paper, what I'm trying to draw and discuss it. Then at some point, then we form a closed trapped surface. um, that yes, so the key here is that at some point it will form a closed flat surface. It's compact, and therefore, yeah, essentially it's compact. And the tension that Penrose highlights is the tension between the non-compactness of the initial Cauchy surface and the compactness of the closed flat surface. So that's basically the argument, that this tension this tension means that we cannot have everything at once. We cannot have a regular manifold with boundary conditions that are prescribed using a non-compact Cauchy surface, and with closed flat surface that is essentially a result of the formation of the horizon. So that's my understanding of the theorem. It's a tension between the compactness of the closed flat surface, let's call it T2, and the non-compactness, the initial conditions.
Why is there a tension?
Did
you assume something about the global structure of the manifold?
Yeah, that it's geodesically complete.
Okay,
So yeah, of course that's part of the point. I didn't want to list all the conditions and go to the technical details. Yeah, so there's a tension between the manifold being geodesically complete, regular, and having both of these features.
But Uri, there is also implicit an assumption that caustics are bad, right? That caustic means geodesic incompleteness.
That's not an assumption, that's a theorem.
Is it a theorem?
Yeah, it's if you are geodesically complete, then you can always, then, I mean, there are no.
There are
It's
no
not,
caustics.
it's not caustics, it's anyway conjugate points.
Yeah.
Yeah.
Okay, but anytime geodesics cross, it's bad.
I mean,
Is that what the theorem says?
I mean, the theorem is this incompleteness theorem. That's what we like to call it rather than singularity.
No,
Okay.
well, I'm answering a different question. I mean, it's just, yeah, basically you can always prove that in a whatever globally I mean, okay. I have to say the fact that global hyperbolicity was never mentioned in this talk, I sort of disagree with it. I even think it should have been in the timeline. Choquet-Brouillat's paper should have been in the timeline.
Which paper?
Choquet-Brouillat's paper on the Einstein equations as whatever, as PDEs.
It's at the Cauchy surface.
There's always an implicit, right?
Hmm?
If you have a Cauchy surface. That's what the.
Well, and anyway, but in a globally hyperbolic space-time, you can always prove that whatever 2 points, they can be connected by a null geodesic, and okay, there's this notion. Well, it's sort of complicated because there's notion of, I don't remember what it's called now, but there are conditions under which 2 points they're connected by null geodesics without conjugate points, and the result is saying that, well, you can't do that without conjugate points. And then, okay, if you unravel all the definitions, the failure is really in the completeness. But it doesn't prove that things have to cross necessarily. I mean, if you actually look at sort of what happens it's helpful to think about what happens when the hypotheses of the theorem are satisfied, like in Schwarzschild. It's not like what happens with the trapped surface that was drawn. They don't actually cross. It's not like the geodesics are crossing, and that's why that's happening.
I think it's useful to think what the theorem applies in the case of Kerr and in the case of Schwarzschild. What does it mean and what does it tell you? And I guess in the Schwarzschild case, it gives you a singularity, like a curvature.
Yeah, there is a closed flat surface like that.
Yeah, of course. I mean, and in the Kerr case, if you have a Cauchy surface intersecting the interior, where you also have just trapped surfaces, then it gives you the incompleteness. That's the point.
I think that's where I'm missing the logic. I have a trapped surface. So I will grant you that this means that geodesics will cross, or what you call conjugate points will exist. And then that SPAD, that comes from some theorem that says, if you got conjugate points, you are incomplete. Is that
Well,
correct?
No, okay, the logic of the proof is, okay, it's slightly different because it is really sort of a topological thing that what happens. So you should think that from this trapped surface, you have an ingoing congruence and an outgoing congruence. And what the theorem actually tells you is that so morally, an ingoing congruence should always meet somewhere. Like that sort of makes sense, that it should always meet. If you think in Minkowski space, the outgoing congruence, it expands. What the theorem tells you is that it can't keep expanding, is that it has to meet. And the point is that from this two surface, you actually generate a three manifold, which is closed because you have the ingoing piece that meets and you have the outgoing piece, which by Reshiduri also has to meet.
Yes.
The point is that the reason it can't keep going out is the monotonicity, that theta has to go to zero. It has to meet eventually. And then the point is that this three manifold, this compact three manifold, cannot exist inside of this space-time with a non-compact Cauchy surface for topological reasons. That part of the argument is sort of technical,
Oh,
but
okay.
this is
So that's the part I'm
Yes.
missing.
Yeah.
Okay.
so because if you think in de Sitter, there are closed trap surfaces in de Sitter, but de Sitter is geodesically complete. And the reason is really because de Sitter is S3 cross R, not something non-compact cross R. So it's really this last part. But the point is that all of this is baked into a contradiction argument. So you can't actually think that this has anything to do with the actual spacetimes under consideration. So it actually tells you nothing about why the incompleteness is really there. So what Christoph was saying is that in Schwarzschild, you actually have a singularity. In Kerr, the singularity happens in a region which is not globally hyperbolic, so it doesn't even satisfy the hypotheses of the theorem. The incompleteness is because of the Cauchy horizon. But you'll never see this, you'll never be able to understand that difference by thinking about caustics. That's the point I'm making. It's sort of, it's a roundabout
I mean,
contradiction.
it's sort of a soft, it's a soft argument, and I think that's how it should be also seen. But
It's a what kind of argument?
Soft.
it's a soft argument, it doesn't require any.
It's an argument why there should be a singularity in solutions, like.
Well,
But again,
why there should be
singularity-
something, why there should be something. It
Something,
doesn't tell you
Right,
it's a
either
singularity
singularity or incomplete.
or incompleteness,
Yeah,
but it doesn't tell you
Right,
why.
right.
Yeah, and so maybe let me go back to
Mhm.
sort of the question about Newtonian mechanics. I think one of the reasons why whatever happens in Newtonian mechanics is more difficult is because there are no soft arguments known there for why when singularities happen. I think there everything is sort of more difficult, and okay, the fact that GR has this structure that lets you find this, let's face it, the paper is like 2 pages long.
Right.
So it's not that difficult finally. Okay, obviously it's a great paper, but in the grand scheme of things, there are much more sophisticated things that people have done. In Newtonian mechanics, as far as I'm aware, there's no such easy result for saying that singularities have to happen.
As certainly
Right,
not
so-
like an open condition.
Yeah, not like an open.
My understanding is that this is a consequence of causality. And the fact that we have some upper bound on the angular momentum.
Well, it's a consequence of all the.
Yeah, sure. But what is the, yeah, I'm trying to extract the essence.
Angular,
That's my impression. Maybe it's,
I don't think this has anything to do with angular movement. What does this have to do with angular movement?
well, again, people thought back then that if you can rotate fast enough, you will balance the collapse.
No, but sort of already, if I just perturb Schwarzschild and then I'm not rotating very fast, then
Yeah, that's the thing. Yeah, you're not, but perhaps if you could rotate fast enough, you could balance the collapse. I think that was the
well, maybe you can, but still, I don't see those seem like disjoint statements. I mean, because I mean, the idea of this result was to apply it to something that is nearly spherically symmetric, right? You think that Schwarzschild is or Oppenheimer-Snyder, right? Because Penrose, well, there's another funny comment that actually
That doesn't apply.
yeah, this result doesn't actually apply to Oppenheimer-Snyder because
Right.
Oppenheimer-Snyder is not smooth across the boundary of the star. But okay.
Well, you could do limited and Bondi and then it would.
Well, there, I mean, okay, it does apply, but it doesn't apply as written anyway. But you know, if you're sort of nearly spherically symmetric, then I don't see what angular momentum preventing collapse has to do with this.
I mean, somehow, I think, yeah, I think it tells you that, again, right? I mean, what he got the Nobel Prize for, that it's an open condition, named having a trapped surface. So it actually gives you an open set of initial data, which have this incompleteness. I think that's what it tells you that they
Yeah,
actually-
yeah.
That and this Oppenheimer Snyder gave you one example, and actually now this generates an open. I think that's.
Okay, yeah,
that's
So
how I-
there are, right, so I just want to say there are such results in Newtonian mechanics, but as far as I'm aware, they actually use the PDE in a way that this uses that the Einstein, well, it uses that the energy momentum tensor has some sign, that there's an energy condition, but so like in Newtonian mechanics, there are results saying that under certain conditions, like if you look at like a fluid coupled to Newtonian gravity, that a singularity forms in finite time, and just like the density of the fluid blows up. But as far as I'm aware, those are much more difficult and were discovered later, and they involve actually studying the PDE. I think Sedaris.
Okay, so yeah, but
You made this comment that de Sitter has closed trap
It does,
surfaces,
yes.
but is complete,
Yeah.
and that has to do with the fact that it's S3 cross R.
Yes,
So if you look at cosmologies with compact spatial hypersurfaces,
yes.
do you have the same situation that you
Well,
have
they're
trap surfaces, but you'll be geodesically complete?
well, so for other cosmological models, you are not complete because you have a Big Bang. But that's different. I mean, that's the Hawking singularity theorem. So in sort of in cosmological models where you have spatially compact Cauchy surfaces, then you should think about different types of incompleteness. It's just
Which
that
maybe
this,
you were going.
yeah, exactly.
yeah,
So
yeah.
let's
yeah, sorry for derailing.
yeah, so we need to wrap up, so that's exactly where we are heading to, the Hawking and Penrose singularity theorem. I have just a few minutes. So let me just say a few words. Again, I hope the experts can correct me if I'm missing essential ingredients, but I just, again, I want to highlight the main points, at least in my mind. But so basically, this picture is really based on the notion of gravitational collapse into a singularity or some problem in the future. And Hawking wanted to generalize it to a more general situation, in particular cosmological singularity in the past. So there had to be some modification of the theorem. And let me mention just the important ingredients. So one condition in the theorem is that there are no closed finite curves. So my understanding is that this is supposed to replace the condition that any finite or null geodesic in this situation ends up in the past at the Cauchy surface. So in a situation where we have in a cosmological situation when we have an expansion, we don't have this condition. So we need something like that. There are no closed finite curves. The second condition is the strong or null energy conditions. The third is the generality condition that I mentioned briefly earlier. So for null rays, it would be something like that, R mu mu. For finite geodesic, it would be R mu mu, U mu, not equal to 0, at least at one point on the ray. And my understanding is that ensures that there is a caustic, so that the trapped surface will be compact. I hope I got it right, but that's my understanding. And the fourth condition is that trapped surfaces although there could be alternatives to that, like a compact space-like surface. So again, the tension is between having some compact surface in the manifold and the hyperbolic nature of the entire manifold.
Sorry, here U is timeline.
Yeah, it's timelike, and there is another condition for null.
So,
Right.
sorry, then how is de Sitter not an example? How, what? De Sitter
Um,
satisfies all these things, doesn't it? They're equal. Well, if that's a timeline factor, then it's not reaching.
But there is another condition, a little bit more complicated for null. For null, I can write it down. Yes, I'm not sure.
You need both?
You need both.
Oh, okay.
Yeah, I didn't write it down because just to keep it simple. Okay, so yeah, I think we are basically running out of time. I wanted to make a comment about personal opinion on what is theirs, what is the what can we do with that, but before that, maybe I'll see if there are any questions or comments that other people might have.
I was really curious to hear your perspective on angular momentum or intermental story, but I don't think you had enough time to get to it. Could you just like?
Well, I said what I had to say. I have something to say about torsion if people are interested. Okay.
Maybe we
Yeah.
can run over by 10 minutes for
Keep
today.
going.
Yeah,
Yeah, if people can.
Yeah,
feel
we
free
need
to-
some time to rearrange the room,
yeah.
but otherwise just keep
Yeah.
going.
Yeah, okay, and if people leave, yeah, I won't be offended, but yeah, so what does it tell us? We don't want the singularity then, right? So what do we do? So, well, what you read in the literature is that eventually quantum effects will have to kick in. Well, more generally, when we have a singularity in physics, it tells us that there are degrees of freedom that we are missing. Right, so something is missing, and so we read in the literature that probably quantum mechanics kicks in at some point, well, quantum gravity, and so on. And what I want to suggest is that it may not necessarily, we may not necessarily have to go all the way to quantum mechanics and string theory and blah, 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 for the sake of singularity itself. If we want quantum gravity, we'll have eventually to go to string theory or alternative for that, but for the sake of the singularity, I want to suggest that we may not have to go all the way there. Well, it was mentioned by Peter that perhaps we should not take the rotation moment to zero, and indeed it might be the case. I want to describe the idea through an example. The example of tau knot spacetime. So I will not give the full details of tau knot, but it is essentially it's a very interesting solution. It's a solution with no curvature singularity. And the reason is that essentially the 1 over r to some power behavior of the curvature is replaced by 1 over r squared plus n squared. Not being careful about the power, so here n is called the knot parameter. So that it's not singular at 0. This knot parameter is the gravitational equivalent of a magnetic monopole. And of course, in addition, there is a mass parameter. So the solution is described by 2 parameters, the Schwarzschild mass and the knot parameter. And we can think about it as the gravitational analog of a diode. So it has this very interesting feature that there are no curvature singularities, but there are conical singularities. There are conical singularities, which are the analog of the Dirac string. In this case, they are called the Meissner string. So what do we do with that? Meissner had the idea to cancel the singularity in the following sophisticated way. We can rotate the singularity around. And what we can do is join together the regular parts of each solution. So as to generate a solution that is regular everywhere. This is known in electrodynamics as the Wu-Yang monopole, where the two regular parts of the Dirac string solution are joined together. Although Meissner discovered it before Wu and Yang in electrodynamics. And what needs to be, we need to make sure that the solution is that everything is alright on the equator, that it's regular and differentiable. So this requires the identification of time on the circle. So that requires, that means that we exchange conical singularity by a different pathology, which is a closed time and curve. So this is why this solution is considered pathological, and this is how it fits into the singularity theorem. There is a closed time and curve. And how is it related? Yeah, so what is the suggestion? And any questions about it? It's very brief, but I hope that just the essence of is conveyed. So a couple of weeks ago, we heard from Kip Thurn that the Einstein equations can be described in the form of the Maxwell equations. So roughly speaking, and in being very imprecise, the Einstein's equations can essentially be written as a Gauss law. Well, here J is essentially constructed from the stress tensor, and F is constructed from the metric and the curvature. We also have the Bianchi identity, which translates into dF equal to 0. Okay, just
Sorry.
yeah, I'm being imprecise, but that's essentially the statement.
Was it a full Einstein's equation or the?
Yeah, that's part of where I'm being imprecise, but at least asymptotically.
Okay.
But yeah, but it can be extended in a way beyond the. So now, as I mentioned, the NAT parameter is considered as the gravitational magnetic analog of the gravitational analog of a magnetic charge, namely, and is essentially an integral over dF over the volume. However, in Einstein's gravity, this is 0 by definition. So the tension is, in a sense, the way to describe the problem with this is that, in a sense, we don't know how to source this conical singularity, this string singularity. And the trick of tying things together on the equator is essentially using diffeomorphism. The identification of time on the circle is essentially diffeomorphism. So this trick is essentially using the stress tensor to resolve this problem. But what I want to suggest is that this is not the right way to do it. We really need to understand what is the gravitational magnetic source. In GR, by definition, we don't have it. But there is a way to do it, but by introducing torsion. So in material with torsion, we will have a source for this string singularity, and we might be able to construct a solution in a theory with torsion that is free of singularities. So that is my 2 cents on the problem. Of course, it remains to be seen, namely, to be seen if that's correct, namely to construct the explicit form of the torsion that balances the string singularity. And so, yeah, I want to emphasize that the problem of evading the singularity and the problem of understanding how to source it are essentially the same thing. If we understand how to source it, we'll also be able to cancel it using some gauge freedom. And yeah, as I mentioned just this morning, I was thinking that it might be the case that this torsion is related to the rotation parameter. Indeed, torsion is rotation, right? So, yeah, perhaps we can look at this later and see if indeed the rotation is related somehow to the torsion. And yeah, so this is something I've been thinking about in the last couple of years. And yeah, I think I will end here.
I was confused with this torsion part. I thought the top knot solution is torsion free,
Yeah, it's
but
torsion
you
free.
still have.
What I'm saying is that a way to describe the problem with tau knot is that there is nothing here to balance the singularity. On this side, there is a string singularity,
Okay,
and there is nothing here to balance.
okay, okay, I see.
Yeah.
Okay. I'm happy.
Yeah, it's really, I find it remarkable that this solution has no curvature singularity. So yeah, that's basically what I'm trying to say. And perhaps there is another way, alternative to Meissner, to resolve the string singularity, such that, and I think it also kind of makes sense. So torsion, we can think about this torsion, additional torsion degrees of freedom as additional forces. Sometimes it's called fifth force in dark matter literature. So, so that would be a force that will balance the gravitational collapse, perhaps. Yeah. Anyway, that's only my.
So I have a question on the Meissner string.
Yeah.
So in top knot, basically you get the effect of a mass current without actually having a mass current, right? It's vacuum except for the string.
Yeah.
So you need a mass current for you to have gravitomagnetism. What is the physical interpretation of the string? Is there mass flowing on the
Yeah,
north pole?
that's exactly the point. There is no physical
Okay,
interpretation.
so
We don't know how to source it.
It's like a current,
Yeah, but
but current without mass.
It's a current without a source that we know how to write to solve. There is no current. There is no.
is it going from the
Well, in
article?
electrodynamics, we can have currents without
Yeah.
charge.
Right. Yeah.
Basically, what you do is you send
No, but
positive
it's,
charges.
it's a monopole. It's a monopole. So it's
Okay.
not just it's a yeah.
Right.
It's really like a magnetic monopole moment,
Yeah.
and we don't have it in general
Right,
by
right.
definition. So yeah.
So if you've got torsion, which I know very little about, you can still satisfy Einstein's equations.
No,
It's already
yeah,
outside.
it's called the well, there are different ways to generalize it, but in principle, it's called Einstein-Cartan theorem,
Ah,
and it's a Riemann-Cartan manifold. It's not Riemannian manifold anymore. It's
okay. And in the language of Raychaudhuri's theorem, what will change?
yeah. So I'm not completely sure. That's what we are discussing. It seems to me like that Raychaudhuri doesn't rely on Einstein gravity and Riemannian manifold. It's just the fact that there is an affine connection. So I believe that it will generalize, perhaps, yeah. I'm not sure, but I believe that it can generalize perhaps straightforwardly, and perhaps the rotation parameter will be related to the torsion. But
right.
yeah, we can discuss it. It's something I just thought about this morning.
Okay. One of the things that happens is that the Christoffel connection is no longer symmetric. So it has an antisymmetric piece.
Right.
So that will trickle down into the Riemann tensor because that's gamma, gamma, del gamma kind of terms.
Yeah.
So then that will trickle down then into the Raychaudhuri equation because it has also contractions.
It looks like it will make an omega.
Right, absolutely. Yeah.
Whether and perhaps few other terms that are lost
exactly.
in the derivation.
Right.
Yeah.
Yes.
Okay.
Like you were mentioning as well, there are evolution equations for the vorticity, the rotation, as well as the expansion. The shear. In Raychaudhuri's equation, we've not looked at those.
Yeah.
Those will also have terms that will
New terms.
likely have terms that will have torsion. So
one other question.
Mm-hmm.
So a space-time with torsion, is it still isotropic, or does torsion automatically pick an axis around which the torsion?
Helen.
Yeah, Ellen is right. Yeah.
Is it isotropic? Can it be isotropic, homogeneous, and yet torsioning away?
I think you can make it at least homogeneous.
You can. Homogeneous, I can believe, but I'm
Yeah.
just wondering whether it picks an automatically an axis associated with the torsion.
And my intuition is that you can still
Isotropic.
yeah, for example, well, it's only an intuition, but for example, this is a magnetic monopole.
Yeah.
And if I'm right and it can be sourced with torsion, it means that we can have a spherically symmetric homogeneous solution. But that's just an intuition.
Yeah, but a magnetic monopole has a direction, right? The whatever that little, oh, maybe
No, it's
not,
not. It's a
maybe
monopole.
not.
It's
It's a
not
monopole.
dipole.
You're right.
Yeah.
You're right. You're right.
Yeah.
I'm keep thinking of the dipole. Yeah.
Yeah.
Okay.
I also think if mass current is going to.
Yeah. No. Good.